So we're going to finish up section 11.7 by talking about logarithmic equations. Now overall, there's going to be two different ways we can solve logarithmic equations. One of them is nice and straightforward. If you have the log of A equals the log of B, that is two logarithmic expressions that are equal to each other, then magically you can get rid of the logs and you end up with A equals B. Now, not everything is going to work this way. Sometimes you have to work things another way. So there's going to be two methods by which you can solve logarithmic equations. This is what I call method one. If you can make it work like that, that's great. Method two is this. You're just going to rewrite your equation. Rewrite the equation, and I'll abbreviate that using exponents. And I think on the top of your last test, I suggested that you write down this right at the top. It's still good to know. It's still good to have. Now, there's one thing that's going to be different about solving logarithmic equations as opposed to exponential equations or quadratic equations, and that is you have to check your answer. It's no longer just a good idea. You have to check your answer because sometimes your answers just aren't going to work out. So check your answers. And there's going to be one, at least one, on the test where maybe one of the possible answers will work and the other one won't. But as a reminder, what can go wrong is that you can't take the logarithm of a negative number. So let's remind ourselves what the graph of the logarithm looks like. Y equals log of x. And take a look at this graph. Notice that it starts out at 0. This graph doesn't exist at 0 or to the left of 0. It's always a little bit to the right of 0. So you can't take the log of a negative number. And that's really what you're worried about when you're checking your answers. So let's start out with example E here. Log base 3 of 2x minus 6 equals log base 3 of x plus 4. Okay, looks okay. Now this is tailor-made for this first method. You've got the log of something equals the log of something else. Now there's a magic step that I'm going to kind of skip here. And maybe after a little bit I'll come back and fill it in. But if you want, leave a little space here and just come down. We're going to get rid of the logs. 2x minus 6 equals x plus 4. Now later on I'll show you what the magic step is that gets rid of the logs. And if you want to show that to me as part of your work, that's an extra credit point. So do be on the lookout for that. But right now, this is pretty easy. This is just a linear equation. Probably the simplest thing to do is to subtract x from both sides. And then maybe, I don't know, add 6 to both sides, right? What equation pops out of this? What do I end up with? X equals 10. Nice. Now we have to check it. So if I wanted to check it, if I put in the 10, I'd have log base 3. 2 times 10 is 20, minus 6 is 14. So I have the log base 3 of 14 equals, well, the log base 3 of 14. Well, that's true. Now, it doesn't matter exactly what the log base 3 of 14 is. It's certainly going to be true. You could check that if you really wanted to, or you could calculate log base 3 of 14. And I'll remind you how to do that on your calculator later. But for right now, let's try another one from example E as well. And that is log of 3x plus 5 equals log of 2x plus 6. Okay. Once again, you've got the log of something equals a log of something else. That's perfect. That's exactly what we're looking for. Does anyone remember what base logarithm we're dealing with? 10. Thank you. So you don't have to write it, but it's understood to be log base 10. That's good to have for later. But because these things are equal, Pfeiffer, what else can I say is equal? What else looks like it has to be equal? Maybe simpler.
I'm not sure, sorry.
All right. Some help? Thank you, Heba. The logs of these are equal, so these have to be equal. So it's just 3x plus 5 equals 2x plus 6. Wow, that one's not too bad. What from there? Solve for x, good. So because 3 is bigger than 2, I'm going to move my x's to the left-hand side. So I'll subtract 2x from both sides. How about the y's? Or if I'm getting x's over here, I'll put the constants over here. Wow. What do I end up with? X equals 1. Nice. X equals 1. Does that work? If I put in a 1 here, I get the log of 8. If I put in the 1 here, I get the log of 8. So it does check. So wow.
That was easy.
Yeah. Pretty nice. Pretty nice. Now, they're not all going to stay that easy. Sorry. I wish that were true. Let's take a look at example F. So log of x squared plus 2x equals the log of x squared plus 8. Why don't you see what you can do with this one? If you're watching this at home, then pause the video, unpause it after you've answered it, but see what you can do.
No, they're just equal.
Meaning what? I mean they're just equal. Equal to what?
To each other.
All right, so let me share with you what is the magic that's happening here that's going to make this logarithm disappear. And it's one of the properties that you had with logs. It was one of the inverse properties. We had b to the log base b of x was equal to x. And it's kind of a similar property to log base b of b to the x equals x. So when you have an exponential function to a power of a logarithmic function, and they share the same base, then those things cancel each other out. So right here, noting that this is a base of 3, I could say, oh, well, let's take and raise both sides to the power of 3. Log base 3 of 2x minus 6, and then 3 to the log base 3 of x plus 4. That's what's canceling out the logs in these things. It's not just, you can't just divide out the log. It doesn't work that way. I mean, if you do this, you get an extra credit point. If you divide out the log, I'll have a hard time not taking off a point. All right, it's just wrong. You can't divide out the logs. So like here, I take 10 to the log base 10 of 3x plus 5, and that's going to equal 10 to the log base 10 of 2x plus 6. So this inverse property of logarithms is what's allowing you to actually solve this. This is a bonus point. If you wanted to just go from here to here, that's fine. But please do not cancel out those logs. You'll make your instructor pretty happy. So 10 to the log base 10 of x squared plus 2x equals 10 to the log base 10 of x squared plus 8. Those things cancel each other out, and I'll be left with x squared plus 2x equals x squared plus 8. Suggestions on what to do to solve? Any ideas? Second power?
Yeah.
All right, so let's cancel out the x to the second power first. And we can do that by subtracting x squared on both sides. And that's kind of nice, because that just leaves me with 2x equals 8. And then I think you said divide by 2, x equals 4. Great. Ah, well done. Thank you, Madison. We got to check it. If I put in a 4 here, I end up with, well, 4 squared is 16. 2 times 4 is 8. 8 and 16 gives me 24. Okay, so I end up with a log of 24. If I put in a 4 here, 4 squared is 16 plus 8, 24 again. Log of 24 equals 24. So it checks. Doesn't matter exactly what the log of 24 is. You get the log of 24 on both sides. Whew. Looking good there. Looking good. Now, so far, these have been pretty straightforward. Let's throw a little bit of a curveball into this. Let's look at the second part of example F. Log of x minus 7 minus log of x equals log of, what's that, 3 over x? Yeah, 3 over x. Now here's something that happens all the time. People see logs on this, they're like, oh, I'll just cancel out all logs. You just can't do that. It does not work this way. That's why I showed you here in example F and the other examples from E that what's getting rid of this is really raising both sides to that power. And it's only really going to work the way you want when you have a log of something equals a log of something else. Is that what I have here? No. Carl?
Are we doing F2?
Yeah, second one in F.
Isn't it log 6 in the middle?
Is it log 6? Let me see here. Oh, it is a 6. Okay. Thank you. There we go. Never happened. Awesome. Thank you, sir. But I still have the same problem. I don't have the log of something equals a log of something else. Here's where you get to use your properties of logs, the stuff that we've spent time on in section 11.6. So how do I clean this up? What do I do so I can rewrite this using one logarithmic expression? There was actually a problem on your last test. Reverse it using what rule for logarithms?
Division.
Yeah. So our quotient rule for logs. So this becomes a log of x minus 7 over 6 equals a log of 3 over x. Nice. So now you've got the log of something equals a log of something else. I'm not going to bother doing that exponentiation step this time. It's just going to be x minus 7 over 6 equals 3 over x. Now what? Now you have what's called a proportion. You have one fraction equals another fraction. So what you could do is cross multiply. This times this, this times this. It only works when you have two fractions. You can't have three fractions, etc. It only works with two fractions. X times x minus 7 equals 6 times 3. Whew. Finally, something we can get our hands on. A quadratic equation. Suggestions. How will we solve this quadratic equation?
Factor or no factor? No.
It will factor.
Bring the 18 together.
Yeah, you got to bring the 18 to the other side. X squared minus 7x minus 18 equals 0. Factoring works when you have a 0 on one side. When you have something times something equals 0, that's when you can kind of divide and conquer. That's when you know that at least one of these has to be 0. Stephanie, help me out. I know one of these has to be a positive and one of them has to be a negative, because a positive times a negative would be a negative. Two numbers that multiply to negative 18 and add to negative 7?
One of them is 9, one of them is 2, so it would be 9, positive 9 minus 2.
Close. The larger one has to have this sign.
Negative 9 positive.
Negative 9 and positive 2. Good. So you've got this times this equals 0. One of those has to be 0. That's the only way you're going to get 0 as a product, is if when you're multiplying something that one of them is 0. So either x minus 9 equals 0, or x equals 9, or x plus 2 equals 0, or x equals negative 2. Whew. Wow. Ah, well done. Oh, you robbed me of my fun. Usually I wait a few seconds and I'm like, okay, take 2 points off your paper. Because you got to check it. It's literally worth 2 points at the end. I need to see you check it. So let's see. We'll check. And we'll check again. So we'll check x equal negative 2 to start with. And I run into a problem right away. Can anyone see what that problem is? Yeah, log of negative 9. Uh-oh. You can't take the log of a negative number. You can just stop right there. We're done. This one doesn't work. Doesn't check. It's not that this is a negative number, it's that you end up taking the log of a negative number. That's the problem. How about x equal 9? Well, we end up with the log of 9 minus 7 is the log of 2 minus the log of 6 equals the log of 3 divided by 2. No, 3 divided by 9, sorry. Log of 3 divided by 9. So at the minimum, you're looking to make sure you don't have the log of any negative terms. That's the minimum. Nor can you have a log of 0. If you wanted to, you could check it on your calculator numerically. This does work. If you really want to check it a little bit more, you could say, all right, well, that's really the log of 2 over 6 equals the log of 3 over 9. You're just using your quotient rule here. And this has to be true because you have the log of 1/3 both times. So it checks. This is what's called an extraneous solution. We've seen that before in this class. So on your exam, it's enough to just kind of cross that one out. Let me know, yeah, I've checked it. I do want to see the checks, though. So do pay lip service to the checks. But sometimes you can just tell right away. It's like, oh, yeah, that one's not going to check. Okay.
Hey, can you help me out with something?
Yeah, please. What you got?
Can you explain to me why you put the log 2 over 6 because that keeps subtracting them?
Oh, it's one of your rules for logarithms. Let me remind you. So recall log of, we'll do a over b, is the log of a minus the log of b. Log of the numerator minus the log of the denominator. Or you could use it in the other direction. When you have this minus this, you could write it as the log of that over that. So just taking this and running it the opposite direction. So that's literally what we did with that last one there. So appreciate the question there. Thank you. Let's move on to example G. Log base 4 of 2x minus 1 What's different about this one than our other ones? There's only one logarithmic term. You don't have a log on both sides. You can't use method 1 for a problem like this, at least not the way it's written. So, Fortunately, we had a method 2, and it was to rewrite this using exponents. So let's rewrite that using exponents and see what that gives us. Who wants to take a crack at that? Kez, all right. Thank you. Perfect. So if you rewrite this, it's always the base to this power. 4 to the 4th power equals 2x minus 1. We'll take out our calculators and find out that 4 to the 4th power is 256. Add 1 to both sides. 257 equals 2x. Divide by 2. 257 divided by 2 equals x. Perfect. Charlie? Ah, thank you, sir. Yeah, we got to check it. You have to check it. If I plugged it in, log base 4 of 2 times 257 divided by 2 minus 1. Now, I guess there's a couple different levels in which you have to check it. 257 over 2. The big thing you got to make sure is that when you take the logarithm of your answer, you don't get a negative number. Now I can go a little bit farther on this one if I wanted to. That's log base 4 of, well, the 2's cancel, right? If those cancel, I end up with 257 minus 1, and I know that that's positive. I don't really have to go any further. You can go a little bit further if you want. Minus 1 equals 4. And verify that log base 4 of 256 is 4. So the bottom line is that it checks. So that solution does work. Let's try the last of the ones in example G. And I wanted to get around to example I if we can get a chance. So it's log base 24 of x minus 2 equals 1 minus log base 24 of x. Okay. Well, we have logs on both sides, but the problem is that the number 1 there isn't part of a logarithmic term. And Mackenzie's all like, oh man, is this going to be a method 2 problem? And it is. The reason it's going to be method 2 is because we can't easily write it in this form where you have the log of A equals the log of B. If that's the case, great, use method 1. If it's not, then you have to rewrite it. But to rewrite it like this, we first have to rewrite this equation so that I have just one logarithm on the left-hand side, or on one side. But for us, it looks like it's convenient to put this on the left-hand side. I'm going to move that term to the left-hand side because it's going to get rid of the negative here for me. So it's going to be log of x, or log base 24 of x plus log base 24 of x minus 2 equals 1. And it's a little closer to what I need, but I still need to write this with one term. Suggestions. How could I write this with one term? Yes. This is your product rule. So going back to Kez, your question just a minute ago, let me add this as well. Log of A times B is the log of A plus the log of B. So we're going to use this in the opposite direction. We're going to build this up a little bit. The sum of the logs becomes the log of the product. That's the key step here. One of two key steps, I would say. Log base 24 of x times x minus 2 equals 1. Let me distribute that x. X squared minus 2x equals 1. Why don't you take a second and see if you can't rewrite this using exponents. This is where I needed to get to. I needed to get to a logarithmic equation that just had logs on one side and the constant on the other side. So I can rewrite this using exponents. Cam, what do you got? What's this going to look like when I rewrite it using exponents? Perfect. 24 to the first power equals x squared minus 2x. If I move the 24 to the right-hand side, I get 0 equals x squared minus 2x minus 24. And, well, again, that's going to factor. Oops, let me zoom out a little bit. Let me bring that up over here and finish it off here. Thanks, Gavin. George, maybe you can help me factor this. I know I need an x and an x. And because that last term is negative, one of these has to be negative, one has to be positive. What are the two numbers that fill in there? Two numbers that multiply to negative 24 and add to negative 2. I'm sorry. Some help? Negative 6 and positive 4. Yeah. To jump down to the solution, x equals 6 or x equals negative 4. Great. So, good with that one? I got to check it. Which one can I get rid of right away? Negative 4. All right, that one's going to cause a problem right here. Over here, well, let's see. If I plug in a 6, that's okay. 6 is okay here. So at the very least, 6 doesn't create any problems. And if you did check it all the way, you'd find that that one works. But this one is, again, extraneous. I know that we're kind of running up against the clock here, but let me just go through example I with you. We're not solving these things. I just want to go through with you, decide what you would use to solve these things. So method 1 problem is when you can write, hey, log of A equals log of B, just get rid of the logs. Method 2 problem is where you're going to rewrite using exponents. So that's when you have log base A of x equals y, and you rewrite it as a to the y equals x. So my question to you is, what type of problems are these? And let's just do it together real quick and knock it out. Is the first one a method 1 or method 2? Yeah, that's a method 1 problem. How about the next one? Method 1 or method 2? 2, because this is not part of a logarithmic term. Now, before you use method 1, you'd have to bring these two terms together like we did with our last one. Like Antonio did. Brought those two together as a product. So that'd be a method 2. How about the second one, or the third one? Again, that term doesn't have a logarithm around it, so that's going to be a method 2 problem. This one's a little tricky. Let me get you started on that one. That's log of 7x minus 12. I would multiply both sides by the denominator. That give me 2 log of x. This is not method 1 yet. It becomes method 1 when we use the power rule for logs. If I move that x into the exponent, now I've got log of 7x minus 12 equals log of x squared. Now finally that's method 1. Yeah. How about this one? Method 1 or method 2?
2.
Method 2. Method 2. Method 1 or method 2?
Method 1.
Yeah, it's not method 1 yet, but we're only one step away from method 1, right? You could rewrite this as log of x times x minus 5 equals log of 6. And now that's method 1. How about the last one?
2.
Yeah, this negative 1 there isn't part of a logarithmic term, so that'd be method 2. So try and keep in mind these examples, what we're doing, what makes the difference between method 1 and method 2. Come on, go the other way. There we go. Because you're going to need to solve this for yourself when you're working on an exam. Comments or questions on the last one? All right, thanks for your extra time here, and see ya!